Welcome to the Deep Dive, your shortcut to being truly well-informed, packed with surprising facts and engaging insights. Today, we're embarking on an ambitious deep dive into the foundational elements that power almost every digital experience you encounter daily. System design. Think of it as peeling back the curtain to see the intricate engineering magic behind the apps and services you love, understanding not just what these digital giants do, but how they do it.
That's right. What you're about to hear is the invisible choreography that makes your digital world hum along seamlessly. From that instant message reaching its destination, to your shared documents staying perfectly synced across devices, and even that quick local delivery appearing at your door, it's all thanks to meticulously designed systems working behind the scenes.
Okay, let's unpack this. We're going to explore how these digital systems are built to be robust, incredibly scalable, and lightning fast, despite immense complexity. You'll gain a practical understanding of the why and how behind this digital world, covering everything from ensuring your messages get where they need to go, to sharing photos, collaborating on documents, and even ordering everyday essentials. It's going to be a fascinating journey into the engineering decisions that shape our online lives. So let's kick things off with a cornerstone of modern distributed systems: the distributed message queue. Imagine it as a super efficient digital post office, but instead of physical letters, it handles messages between different parts of a complex software system. It's essentially an asynchronous communication backbone, enabling what we call loose coupling, which is just a fancy way of saying different software services can talk to each other without being rigidly tied together. This makes the whole system far more resilient and scalable.
What's fascinating here is that this digital post office acts as an intermediary buffer. Think of it like a shock absorber. When one part of the system sends a message, it doesn't wait for the recipient to be ready. It just drops the message in the queue. This means if one service goes down temporarily, the messages don't disappear, they just wait in line, and the whole system doesn't collapse. It greatly improves fault tolerance and overall system reliability.
Let's talk about the core functional requirements for such a system. You need to be able to send message, queue name, message payload. This means that when a producer, say, an app generating an order, publishes a message to a specific queue, the system must acknowledge receipt once that message is durably stored. That durably stored part is crucial. It's the guarantee that your message isn't just floating in the air, it's safely tucked away.
And on the flip side, you need receive message, queue name. This is how consumers, like a service processing those orders, fetch one or more messages from a queue. A key, often surprising, part of this process is that once a message is given to a consumer, it becomes temporarily invisible to other consumers. This is a clever trick to prevent duplicate processing, ensuring that only one service tries to handle the same piece of work, avoiding chaos.
Then, once a consumer has successfully processed that message, say, the order's fulfilled, it needs to explicitly tell the queue to remove it. So, delete message, queue name, message handle, means consumers confirm that the message should be permanently removed from the queue after successful processing. It's like picking up your mail and then immediately shredding it because you've dealt with it.
The default guarantee for these systems is typically at least once delivery. This means a message will be delivered one or more times. Think of it as a very persistent delivery person. They'll definitely get the package to you, but they might, knock on your door multiple times. However, a more stringent and often optional guarantee is exactly once semantics, EOS. This guarantees that a message is processed exactly once, end to end. This is a significant feature enhancement because achieving it requires extremely careful coordination between the sender, the queue, and the receiver, making it a true engineering feat.
And when it comes to ordering, message ordering is crucial, especially for things like sequences of events. FIFO, or first in, first out, ordering should be guaranteed within a partition or shard, but not necessarily globally across the entire queue. Imagine a library with many sections. Books are always shelved in order within their section, but the sections themselves might be managed independently. So within a specific segment of the queue, the order you send messages is maintained, but across the entire system, there's no global strict order.
Finally, we need a safety net for problematic messages. A dead letter queue, DLQ, is a secondary queue, a kind of digital quarantine zone for messages that fail processing repeatedly, for example, after a configurable number of retries. This is incredibly useful because it prevents bad messages from clogging up the main queue, allowing engineers to later inspect them manually and figure out what went wrong, perhaps a malformed message or a bug in the processing service.
Moving on to the non-functional requirements, which are just as vital as the functional ones. These are the qualities of the system, how well it performs under pressure. First up, high availability. The system must be resilient to node failures with no single point of failure. This directly implies redundancy across all components and data centers, ensuring your service stays up and running even if parts of it go down. It's like having backup generators and parallel systems running in different locations, so if one fails, the lights never go out.
Next, scalability. The system should scale horizontally to handle a massive number of messages per second, we're talking millions, and a large number of queues. Horizontal scaling is the preferred method here, meaning you simply add more identical machines to handle increased load rather than trying to upgrade existing larger ones. It's like adding more lanes to a highway as traffic increases rather than trying to make existing lanes wider.
Durability is non-negotiable. Once a message is accepted, it must not be lost, even in the event of hardware failure. This is achieved through replication and persistent storage, usually with a configurable retention policy, which could be time-based, e.g. keep messages for 7 days, or size-based, for example, keep up to 1 terabyte of messages. This is the guarantee that your data is safe, come what may.
And speed is paramount. Low latency means both send and receive operations should have minimal delay, typically in the low milliseconds. This ensures a responsive user experience for applications built on top of the message queue. Imagine sending a text. You want it to arrive almost instantly, not minutes later. That's low latency in action.
Security is also a critical concern. We're talking end-to-end encryption for data in transit using TLS, which is like putting your messages in a secure encrypted tunnel as they travel across the network. And also encryption at rest, meaning the data is encrypted even when it's stored on disks. You also need robust authentication and authorization for producers and consumers, so only authorized services can send or receive messages. And for modern systems, mutual TLS, MTLS, for secure service-to-service communication is the standard. This is like when two secret agents meet. They don't just ask for each other's ID, they both present their own, proving their identity to each other before they even start talking. It's the highest level of trust and security between different parts of a software system.
And finally, observability. You need comprehensive monitoring through metrics, such as queue depth, how many messages are waiting, and message throughput, how many messages are processed per second, structured logging to track events, and distributed tracing to follow a message's entire lifecycle across various services. This lets you understand exactly what's happening inside the system, pinpointing bottlenecks or failures in real time. It's like having a detailed GPS for every single message, showing you its entire journey.
The API, or system interface, for a message queue is quite straightforward, mirroring those functional requirements we just discussed. It primarily consists of send message, queue name, message payload for producers to publish messages.
Then you have receive message for consumers to fetch messages.
And delete message, queue name, message handle for consumers to confirm processing and remove messages. Simple, but incredibly powerful foundations for building complex systems. Let's trace the data flow, the journey a message takes through this system. When you send a message, the producer sends the message, which first hits a load balancer. Think of this as a digital traffic cop directing incoming requests efficiently. From there, it goes to a front-end service.
The front-end service is the system's gatekeeper. It handles authentication, validation to ensure the message is well-formed, and rate limiting to prevent any single producer from overwhelming the system. It then queries a metadata service or its local cache for speed to find the leader of the target partition. A partition is essentially a segment of the queue responsible for a subset of messages, and the leader is the primary node in charge of that segment.
Once identified, the front end forwards the message to that leader broker. The leader then immediately replicates the message to its followers, which are exact copies of the leader's data. Only upon confirmation from a quorum of these followers, a minimum number of copies confirming receipt, does the leader send an acknowledgement back to the front end, which then relays it all the way back to the producer. This ensures durability. It's the guarantee that your message is safely stored in multiple places before you even get a confirmation.
The receive flow starts when a consumer sends a request, which also goes through a load balancer and then the front-end service. The front end authenticates the consumer and determines the appropriate back-end cluster from which to retrieve messages.
The consumer pulls messages from either the leader or sometimes a follower. Pulling from a follower can be a strategy for read scaling, distributing the workload more efficiently. Crucially, when a message is sent to a consumer, the back end starts a visibility timeout. This is like a librarian holding a book for you for a few minutes. During this timeout, the message becomes temporarily invisible to other consumers, preventing multiple services from trying to process the same message simultaneously.
If the consumer successfully processes the message, it sends a delete message request, permanently removing it from the queue. However, if that visibility timeout expires before deletion, for instance, if the consumer crashes or takes too long to process the message, automatically becomes visible again for another consumer to process. This mechanism ensures that a message is never lost, even if a consumer fails mid-processing.
And to handle load distribution efficiently, multiple consumers can form consumer groups to process messages from a queue in parallel. Think of it like a team of postal workers sorting mail. Each worker within the group is assigned a subset of partitions, allowing for efficient, concurrent processing and ensuring that messages are distributed evenly among them.
Moving to the high-level design, we have a few key components. The front-end service is a stateless, horizontally scalable layer that handles all API requests. It's responsible for the initial interaction, including authentication, authorization, TLS termination, rate limiting, and routing requests to the appropriate backend cluster. Being stateless means you can add or remove these services easily without affecting the overall system, much like adding more identical cashiers to a busy supermarket.
Then there's the metadata service. This is a highly available service that stores crucial information about queues, such as their configuration, how they're divided into partitions, and their retention policies, as well as tracking where consumers are in the queue, their offsets. It's often backed by a strongly consistent database like Zookeeper, etc., or a distributed SQL database. Think of it as the central directory for all queue information. And for speed, caching at the front-end layer is absolutely crucial to reduce latency when accessing this metadata, preventing every request from hitting the central directory.
The backend service, or broker cluster, is the stateful core of the message queue. This is where the magic happens: message storage, replication, and delivery. It's composed of multiple clusters to handle the vast amounts of data and traffic. It's the actual warehouse where all the messages are stored and managed.
And within those backend clusters, replication and consensus are fundamental to ensuring data integrity and availability. Backend nodes within a cluster use a consensus algorithm like Raft or Paxos for leader election. These algorithms are like highly disciplined accountants who always agree on the ledger's exact state, even if one takes a coffee break. This isn't just technical wizardry, it's what ensures your payment isn't double processed or your message lost, even in a global internet. Raft is often preferred in modern systems for its understandability and strong guarantees, making it a popular choice for achieving consistent data replication.
Let's dive deeper into some technical implementations. For data partitioning, also known as sharding, a single logical queue is partitioned into multiple physical shards to handle extremely high throughput. Imagine a very long single line at a popular store. To serve more customers faster, you split that one line into multiple shorter lines, each with its own cashier. That's partitioning.
The partitioning strategy often involves a consistent hashing scheme on the queue name, or a dedicated partitioning key. This intelligently maps a queue to a specific back-end cluster, or even to a specific node within a cluster. For very large queues, often called hot queues, imagine that one express lane that everyone wants to use the queue itself can be further partitioned across multiple nodes within a cluster to distribute the load even more. Handling hot partitions is a specific challenge. If one partition receives a disproportionate amount of traffic, becoming a bottleneck, dynamic repartitioning or splitting, that hot partition may be necessary. It's like realizing one of your express lanes is getting all the customers, so you quickly open another one and direct traffic there. Another strategy to spread the load more evenly is to add a random key to messages, distributing writes across the partition more uniformly, essentially encouraging customers to spread out among the lanes. For message storage and replication, backend nodes typically use a log-structured storage model, similar to Apache Kafka. Think of it like an endlessly appending notebook. Messages are simply written, one after another, to a commit log on disk. This approach is incredibly efficient for sequential writes, making it extremely fast, as you're always just adding to the end.
The replication model we're discussing is a leader-follower model with synchronous replication for high durability. A producer's send message request is routed to the leader of its specific partition. The leader writes the message to its local commit log, then simultaneously replicates it to a quorum of follower nodes. These are the redundant copies we talked about earlier.
Only once the leader receives acknowledgments from that quorum of followers, meaning enough copies have confirmed they have the message, does it acknowledge the message receipt back to the producer. This ensures maximum durability, meaning the message won't be lost even if the leader fails immediately after. It's like getting multiple confirmations from different safe deposit boxes before you're told your precious item is truly secure.
And to manage storage over time, retention policy is key. Messages are retained based on a configurable policy, say 7 days or 1 TB per queue, after which they are automatically purged. This prevents unbounded growth and keeps storage costs in check. You don't want your digital post office overflowing with old, unneeded messages forever.
Achieving what's exactly one's semantics, EOS, is notably complex and requires cooperation not just from the messaging system, but also from the client applications. It's one of the holy grails of distributed systems, ensuring that even if a message is sent multiple times due to retries or network hiccups, the consuming application processes it just once.
One part of this is idempotent producers. This means a producer can send the same message multiple times, and the system on the other end knows it's the same message and only processes it once. The producer is assigned a unique ID and sends a sequence number with each message. The broker tracks the latest sequence number for each producer and simply discards any duplicate messages, ensuring only one instance is processed. It's like a mailroom clerk who tracks unique package IDs. If they see a package with an ID they've already processed, they just ignore it.
Another crucial piece is transactional commits. For consumer applications that read from a queue and then write to another system, like a database, the consumer can use a transactional outbox pattern. This means the result of the processing and the message offset, where the consumer is in the queue, are written to the database in the same atomic transaction. A separate process then reliably publishes those results. It's like saying, I've processed this order and updated my inventory, and only then will I tell the queue to mark the message as done. All or nothing.
Error handling is also deeply built into the system to ensure resilience. Failed send or receive operations use retries with exponential backoff and jitter. This prevents a failing service from immediately hammering the system with continuous retries. Instead of retrying instantly, it waits a bit longer each time, and jitter adds a small random delay to prevent all retrying services from hitting the system at exactly the same time, preventing system overload.
And as we discussed earlier, DLQ integration comes into play here. Messages exceeding their retry limits are automatically moved to the dead letter queue with metadata about the failure, making it easier for engineers to investigate why they failed rather than these messages just disappearing or endlessly retrying and causing problems.
When it comes to addressing bottlenecks and ensuring scalability, several strategies are employed. The front end is stateless, as we mentioned, and can be scaled horizontally behind a load balancer, making it incredibly easy to add capacity as traffic increases, much like adding more identical storefronts to handle more customers.
Back-end scaling works by adding more back-end clusters. Individual cluster sizes are typically kept relatively small, like 3 to 5 nodes, to maintain fast consensus within the cluster. This keeps the decision-making among the nodes quick and efficient.
For metadata performance, heavy caching on the front end is absolutely critical. The metadata service itself is primarily write-heavy, only during infrequent operations like queue creation or deletion, so reads are the main concern. By caching this information right at the front door, you avoid constantly asking the central directory for information it already knows.
And back pressure is a sophisticated mechanism. If consumers are slow, messages will inevitably build up in the queue. The system can then implement flow control by signaling producers to slow down their message sending. Conversely, consumers can also dynamically scale their own capacity based on queue depth metrics, pulling more messages when needed. It's a bit like a flexible highway system that can tell cars to slow down or speed up based on congestion ahead.
In terms of current industry standards, this design aligns with modern distributed message queue systems like Apache Kafka, Amazon SQS, and Google PubSub, all of which emphasize scalability, durability, and fault tolerance as their core tenets.
For security, Mutual TLS, or MTLS, is the current standard for secure service-to-service communication, ensuring both client and server authentication for every connection. This provides an incredibly robust security posture, making sure only trusted components are talking to each other.
And finally, observability through distributed tracing, like OpenTelemetry, is crucial. It allows you to monitor message flows across microservices, which is a standard practice in modern, complex systems. This comprehensive design provides a robust, scalable, and secure distributed message queue system, perfectly suited for high-throughput, low-latency messaging in a microservices architecture. It truly lets you see the invisible magic happening. #tag design a file storage service like Dropbox.
Okay. Let's pivot from the invisible flows of message queues to something many of us use every single day, a file storage service, something like Dropbox. This is all about making your digital life accessible and synced across devices. What are the key functional requirements here? Well, first, users should be able to upload a file from any device. Simple, right? But the any device part adds complexity.
And naturally, users should be able to download a file from any device. It's all about accessibility across your entire digital ecosystem. You want to pick up your work seamlessly, whether you're on your phone, tablet, or desktop.
Beyond just personal access, users should be able to share a file with other users and view the files shared with them. Collaboration is key in these services. It's what makes them so powerful for teams and families alike.
And a standout feature for many, users should be able to automatically sync files across devices. This means your documents are always up to date wherever you access them without you having to manually move them around. It's the magic that makes your desktop folder appear on your phone.
Now for the non-functional requirements. The system should be highly available, prioritizing availability over consistency. This is an important trade-off. It's acceptable for a file storage system like Dropbox if a user in Germany uploads a file, and a user in the US can't see it for a few seconds. Unlike systems where every read must receive the most recent write, a few seconds of staleness is usually fine for a file syncing service. It's about ensuring you can access your files, even if the absolute latest version isn't instantly propagated everywhere.
It's also vital that the system supports files as large as 50 GB. This is a significant technical challenge in itself. Trying to move such a massive chunk of data reliably across networks introduces many complexities.
And of course, the system should be secure and reliable. We should be able to recover files if they are lost or corrupted. Data integrity and user trust are paramount. Imagine losing your entire photo library.
Finally, the system should make upload, download, and sync times as fast as possible, meaning low latency. No one wants to wait ages for their files to transfer, especially when working on the go.
When we talk about core entities for a file storage service, they're quite intuitive. First, there's the file itself. This is the raw data, your photos, documents, videos that users will be uploading, downloading, and sharing.
Then you have file metadata. This is the information about the file rather than the file content itself. It includes things like its name, size, MIME type, what kind of file it is, like an image or a PDF, and crucially, the user who uploaded it. Think of it as the index card for your digital item.
And underpinning it all, the user, the individual interacting with our system, the person who owns, shares, and accesses these files. The APIs for this kind of service are pretty straightforward. You'll need endpoints for uploading a file, download a file, and share a file. User information, by the way, will typically be passed in the headers, either via a session token or a JSON Web Token or JWT, which are secure ways to identify who's making the request.
Let's get into the high-level design, starting with how users upload a file from any device. For the metadata associated with files, we can leverage a NoSQL database like DynamoDB. Our metadata is loosely structured, with few rigid relationships between different pieces of data, making a NoSQL database a great fit for simplicity and horizontal scalability.
The best approach for actual file upload, especially for large files, is to allow the user to upload the file directly to blob storage from the client. This typically involves a clever, secure three-step process. First, the client requests a pre-signed URL from our backend. Our backend, in turn, obtains this special temporary URL from the blob storage service itself, like Amazon S3. At this point, we also save the file metadata in our database, marking its status as uploading.
Second, the client uses that pre-signed URL to directly PU the file to blob storage. This is where the efficiency comes in. The file itself bypasses our backend services, going straight to the specialized storage, which is far more efficient for large data transfers. It's like being given a special temporary key to drop off a package directly at the warehouse instead of having to send it through the central office.
And finally, once the file is uploaded, the blob storage service will send a notification to our backend using mechanisms like S3 notifications. Our backend then updates the file metadata in our database, changing its status to uploaded. These pre-signed URLs, by the way, are temporary secure access tokens for private resources with an expiration time, offering a secure way to grant temporary upload-download access without altering core permissions.
For downloading a file from any device, the best approach is to use a content delivery network, or CDN, to cache the file closer to the user. A CDN is a globally distributed network of servers that caches content. When you request a file, the CDN serves it from the server closest to you, significantly speeding up downloads by reducing the physical distance the data has to travel.
Similar to the pre-signed URLs for uploads, we can generate a URL that the user can use to download the file directly from the CDN. This URL will grant the user permission to download the file from a specific cache location for a limited time, enhancing security by ensuring the link isn't permanently valid.
When it comes to users sharing a file with other users, a common approach is creating a new table, say, shared files, that simply maps a user ID to a file ID, where the file ID represents a file that has been shared with that specific user.
This way, when a user accesses our site, we can quickly retrieve the list of files shared with them by simply querying the shared files table for all files associated with their user ID. It's like looking up your name on a guest list to see what invitations you've received.
Lastly, enabling users to automatically sync files across devices requires handling two directions of data flow. Local to remote, changes made on your device get uploaded, and remote to local, changes made elsewhere get downloaded to your device.
For local remote syncing, a client-side sync agent, a small piece of software on your device, monitors your local Dropbox folder for changes using OS-specific file system events, such as File System Watcher on Windows or FS Events on macOS. When it detects a change, like a file being saved or deleted, it queues that modified file for local upload, then uses our Upload API to send the changes to the server along with updated metadata. Conflicts, if they arise because two people edit the same file simultaneously, are typically resolved using a last write wins strategy, meaning the most recent edit is saved.
For remote local syncing, we can use a hybrid approach that balances real-time updates with efficiency. We classify files into two categories. Fresh files are those recently edited, say within the last few hours. For these, we maintain a persistent WebSocket connection. This is like an open phone line, allowing for near real-time synchronization, so changes appear almost instantly.
Stale files, on the other hand, are those that haven't been modified in a while. For these, we can fall back to periodic polling since immediate updates are less critical. It's like checking your physical mailbox once a day instead of constantly peering out the window. This balances the need for real-time updates with system efficiency, saving resources for what truly needs to be instant. Now for the deep dives, and this is where it gets really interesting for a service like Dropbox. How do you support truly large files, like that 50 GB example we mentioned? Two critical user experience needs immediately come to mind. A progress indicator so users know it's working and how long it will take. Imagine uploading a huge video without any feedback.
And resumable uploads. This is absolutely crucial for large files. Users should be able to pause and resume uploads. If they lose their internet connection, their browser crashes, or their laptop dies, they should be able to pick up where they left off, rather than starting over and re-uploading 49 GB that may have already been uploaded.
There are significant limitations that come with trying to upload a large file via a single POST request. Think about timeouts. Web servers and clients typically have timeout settings to prevent indefinite waiting. A single POST for a 50 GB file could easily exceed these, leading to a failed upload.
Plus, there are browser and server limitations. In most cases, it's not even possible to upload a 50 GB file via a single POST request due to configuration limits on the maximum size of a single upload. And of course, network interruptions are always a risk, causing uploads to fail completely and forcing a full restart if not handled properly.
And from a user experience perspective, users are effectively blind to the progress of their upload. They have no idea how long it will take, if it's even working, or if the connection dropped. This leads to a frustrating and uncertain experience.
The solution to this is chunking. We break the file into smaller pieces, typically 5-10 megabytes on the client side, and upload them one at a time, or even in parallel, depending on network bandwidth. This chunking needs to be done on the client, so the file is divided before it's even sent to the server or S3.
With chunks, showing a progress indicator is straightforward. We can simply track the progress of each chunk and update the progress bar as each chunk is successfully uploaded. To enable resumable uploads, we update the file metadata schema in our database to include a chunks field. This field tracks the status of each individual chunk. When the user resumes the upload, we check this field to see which chunks have already been uploaded and which haven't, allowing us to start uploading only the missing segments.
But how do we ensure this chunks field is kept in sync with the actual chunks that have been uploaded without relying on the client? We use S3 event notifications. These are a feature of S3 that allow you to trigger a Lambda function or send a message to an SNS topic when a file is uploaded to S3. We can use this to send a message to our backend when a chunk is successfully uploaded. Then our backend updates the chunks field in the file metadata table, ensuring consistency.
This brings us to how to uniquely identify a file and a chunk. When you try to resume an upload, the very first question that should be asked is, have I tried to upload this file before? And if yes, which chunks have I already uploaded? We need to rely on a unique identifier that is derived from the file's content. This is called a fingerprint. A fingerprint is a mathematical calculation that generates a unique hash value based on the content of the file. For resumable uploads, The process involves not only fingerprinting the entire file to get a unique file ID, but also generating fingerprints for each individual chunk. This chunk-level fingerprinting allows the system to precisely identify which parts of the file have already been transmitted and which still need to be sent.
So the steps when a user uploads a large file are quite detailed but efficient. First, the client will chunk the file into 5 10 MB pieces and calculate a fingerprint for each chunk. It will also calculate a fingerprint for the entire file, and this becomes the file ID.
Second, the client will send a DAT-RAY request to fetch the file metadata for the file with the given file ID, which is its fingerprint, in order to see if it already exists, in which case we can resume the upload from where it left off. If the file does not exist, the client will p-post a request to files presigned URL to get a presigned URL for the file. The backend will then save the file metadata in the file metadata table with a status of uploading, and the chunks array will be a list of the chunk fingerprints with an initial status of not uploaded.
Fourth, the client will then upload each chunk to S3 using the presigned URL. After each chunk is uploaded, S3 will send a message to our backend using S3 event notifications. Our backend will then update the chunks field in the file metadata table to mark that specific chunk as uploaded.
Once all chunks in our chunks array are marked as uploaded, the backend will update the file metadata table to mark the file as uploaded. It's worth noting that services like Amazon S3 have a native feature called multi-part upload that allows you to upload large objects in parts, and S3 then conveniently combines these parts into a single object, simplifying much of this chunking logic.
Now, how can we make uploads, downloads, and syncing as fast as possible? We can utilize compression to speed up both uploads and downloads. This is useful if the speed gained from transferring fewer bytes outweighs the time it takes to compress and decompress the file, which it often does for larger files.
Additionally, by sending multiple chunks in parallel and utilizing adaptive chunk sizes based on network conditions, we can maximize the use of available bandwidth. It's like a smart delivery service, adjusting package sizes and number of trucks based on road conditions. The same chunking approach can be used for syncing files. When a file changes, we can identify which chunks have changed and only sync those chunks rather than the entire file, making syncing much faster for minor edits.
Finally, let's consider how to ensure file security. Encryption in transit is crucial. We use HTTPS to encrypt the data as it's transferred between the client and the server. This creates a secure, private tunnel for your data while it's moving across the internet.
And encryption at rest. We encrypt the files when they are stored in S3. When a file is uploaded to S3, we can specify that it should be encrypted. S3 then handles the encryption using a unique key and stores that key separately from the file. This means even if someone were to gain unauthorized access to the storage, the raw files would be unintelligible.
For access control, our share list, or separate share table cache, serves as our basic access control list, ACL. We make sure that we share download links only with authorized users. When a user requests a download link, we generate a signed URL that is only valid for a short period of time, for example, 5 minutes. This signed URL is then sent to the user who can use it to download the file. If an unauthorized user gets a hold of the signed URL, they won't be able to use it to download the file because it will have expired. This adds a crucial layer of security, making temporary secure access possible without permanent permissions. #tag design Facebook's newsfeed.
Okay, let's pivot from file storage to something many of us interact with multiple times a day, Facebook's news feed. This isn't just a list of updates. It's a meticulously crafted system designed to deliver a constantly evolving stream of content. At its core, the functional requirements are straightforward. Users should be able to create posts.
They should also be able to friend or follow people. This establishes the social graph that determines what content they see, forming the backbone of their personalized feed.
And critically, users should be able to view a feed of posts from people they follow, presented in chronological order. This is the main interaction point, the primary way people consume content on the platform.
And to manage that potentially vast amount of content, users should be able to page through their feed. This provides a digestible experience, loading more content as they scroll without overwhelming them all at once.
For non-functional requirements, high availability is paramount, prioritizing availability over consistency. This is an interesting trade-off for a newsfeed. We're willing to tolerate up to 1 minute of post staleness, meaning eventual consistency is acceptable. It's better that you see some version of your feed instantly, rather than waiting for it to be absolutely perfectly up to the millisecond consistent.
Speed is also critical. Posting and viewing the feed should be fast, returning in less than 500 milliseconds. Users expect near-instant updates and fluid scrolling, Any lag quickly translates into a frustrating experience.
And the scale is immense. The system should be able to handle a massive number of users, easily 2 billion. Imagine managing connections and delivering personalized content for a quarter of the world's population.
Furthermore, users should be able to follow an unlimited number of users, and conversely, users should be able to be followed by an unlimited number of users. This means the follower graph must be infinitely scalable without hitting bottlenecks as people connect more and more widely.
The core entities for this system are quite clear. A user, who is a person in our system with their profile and identity. A follow, which is a unidirectional link between users, so I follow you, but you don't necessarily follow me back. And a post, which is a piece of content made by a user, like a photo, video, or text update, shown in the feeds of their followers.
When it comes to the API endpoints, they're pretty standard. You'd have an endpoint to create posts, another to follow people, linking one user to another, and finally, one to view our feed. For viewing the feed, we'd typically use a timestamp as a cursor to represent the oldest post they've seen so far, so each page would return end posts older than that timestamp, enabling infinite scrolling.
For the high-level design, let's start with users creating posts. For our database, we can use any key value store that handles high write volume efficiently. In this application, we'll use DynamoDB for its simplicity and remarkable horizontal scalability. DynamoDB allows us to provision a nearly limitless amount of capacity, provided we spread our load evenly across our partitions, which is crucial for handling billions of posts.
Next, enabling users to friend or follow people. This is a many-to-many relationship, and we can model it as a graph. Typically, for a graph, you might think of using a purpose-built graph database like Neo4j or a triple store. However, given our relatively simple requirements for just tracking follows and followers, we'll keep our system simpler and use a key value store to model the graph ourselves, avoiding the complexities of scaling specialized graph databases if our needs don't strictly demand them.
So we have a simple follow table. To store who is following whom, we'd use the user following as the partition key and user followed as the sort key. This allows us to efficiently query all the users a given user follows. To allow for reverse lookups, that is, getting all the followers of a given user, we can create a global secondary index, GSI, with the reverse relationship, a partition key of user followed, and a sort key of user following.
This setup allows us to efficiently query for important pieces of information. For instance, if we want to check if one user is following another, we query with both the partition key and the sort key, like userFollowing.userFollowed. This is a very simple direct lookup.
If you want to get all the users a given user is following, you query with just the partition key, userFollowing. This is a range query that quickly retrieves all those relationships. And to get all the users who are following a given user, you query the GSI with its partition key, userFollowed, which is also a range query, providing that reverse lookup efficiently.
Now, about users viewing a feed of posts from people they follow, a bad approach would be to first request all the users they follow from the follow table. Then for each of those end-followed users, we request all their posts from the post table via its GSI. Finally, we gather all those posts, sort them by timestamp, and return the results to the user.
This approach is bad for several reasons. First, a user may be following lots of users, potentially thousands. Second, each of those users may have lots of posts. And critically, the total set of posts to retrieve and sort could become very large because of either or both of those factors, making this approach incredibly slow and inefficient for read operations. Imagine trying to gather every single newspaper from every friend's house and then sorting them all chronologically yourself every time you wanted to read the news.
And as for users being able to page through their feed, the details for this and the main feed view are actually addressed in our deep dives to ensure scalability and performance. This is where we uncover the clever engineering solutions to those scalability problems.
So let's jump into those deep dives. First, how do we handle users who are following a large number of users? This problem is famously known as fan out. A single post creation, if not handled carefully, can fan out to create many more read requests or updates to generate a feed.
The solution here is fan out on write, or pre-computing the feed. Instead of computing the feed results at the moment someone wants to read their feed, we compute them at post-creation, or write time. We maintain a pre-computed feed table. When a new post is created, we simply add it directly to the relevant pre-computed feeds of all its followers. This means the read operation becomes extremely fast because the work has already been done up front. It's like having a personalized newspaper printed for every subscriber the moment an article is written.
But this leads to our next challenge. How do we handle users with a large number of followers? Think about celebrities like Justin Bieber or major news outlets. If we pre-compute feeds for users with millions of followers, it becomes impractical due to massive write amplification. A single post from Bieber with tens of millions of followers would mean tens of millions of writes to update all his followers' pre-computed feeds. This is an unsustainable amount of write traffic.
The solution is a hybrid approach, combining fan-out on write for most users with fan-out on read for celebrities. We choose a threshold, say 100,000 followers, to differentiate regular users from celebrities. For celebrities, we add a flag to the follow table, indicating that their posts are not pre-computed. Asynchronous workers that normally update feeds will then ignore these posts, saving massive write operations.
On the read side, when a user requests their feed via the feed service, we first fetch their partially pre-computed feed from the pre-computed feed table. This covers posts from all the regular users they follow. Then, we separately query the post table for recent posts specifically from the celebrity accounts the user follows. Finally, we merge these two sets of posts chronologically and return them. This is done on the fly at read time.
There are crucial trade-offs here. Tuning that threshold is critical. If it's too low, the fan-out on write problem persists for too many users. If it's too high, read performance suffers for too many users, as more processing has to happen at read time. Also, users following many celebrities might experience slower feeds than those who don't, creating a potentially inconsistent user experience. We need clear service-level agreements, SLAs, for different user segments and potentially specific caching strategies just for celebrity posts to mitigate this.
Lastly, how can we handle uneven reads of posts? For the vast majority of posts, they will be read heavily for a few days immediately after publication and then never read again. However, for some posts, especially those from accounts with lots of followers, the number of reads the post experiences in the first few hours will be massive, far exceeding the initial burst.
The solution is to insert a cache between the readers of the post table and the database itself. Since posts are very rarely edited after creation, we can keep a long time to live, or TTL, on the posts in the cache. Our cache can then evict posts using a least recently used, or LRU, policy, ensuring the most relevant and frequently accessed content remains readily available in memory, while older, less popular posts are gracefully removed from the cache to make space. This dramatically reduces the load on our primary database. Hashtag Facebook's post search design.
Now let's transition from viewing feeds to searching them. We're now diving into Facebook's post-search design, which layers an entirely new set of challenges on top of what we just discussed. Functionally, users should be able to create and like posts, which we touched on with the newsfeed.
But the unique and core part here is that users should be able to search posts by keyword. This introduces a whole new layer of complexity, moving beyond simple chronological feeds to finding specific content buried within billions of posts.
And to make those search results truly useful, users should be able to get search results sorted by recency or like count. This means two different dynamic ways to order the vast amount of data, depending on what the user prioritizes.
Looking at the non-functional requirements, the system must be fast, with median queries returning in less than 500 milliseconds. When you type in a search query, you expect near-instant results, not a long wait.
It also must support a high volume of requests, which we'll estimate shortly. And crucially, new posts must be searchable in a short amount of time, less than 1 minute. If you post something, you want it to be discoverable almost immediately.
Importantly, all posts must be discoverable, including old or unpopular posts. For these, we can tolerate taking a bit more time. The system should also be highly available, meaning search functionality is always accessible.
And a key performance consideration: hot data posts that are frequently accessed, perhaps from a viral event, should be served quickly, often from memory. Cold data, infrequently accessed old posts, can be served from disk or remote, cheaper storage. This balances speed with cost efficiency across the entire data set.
Let's do some capacity estimation for a system of this scale. We're talking about 1 billion users.
For writes, specifically posts, we're looking at about 10,000 posts per second. This is calculated simply as 1 billion users making, on average, 1 post per day, divided by roughly 100,000 seconds in a day. For likes, it's even higher. 100,000 likes per second derived from 1 million users making around 10 likes per day over the same time period. That's a massive write throughput.
For reads, we're estimating 10,000 searches per second based on 1 billion users performing just one search per day. Even that seemingly small average translates into a huge volume of concurrent queries.
And the storage requirements are truly massive. For posts over 10 years, that's 3.6 trillion posts, calculated as 1 billion posts per day, times 365 days in a year, times 10 years.
In terms of raw size, If each post is about 1 kilobyte, that's a staggering 3.6 petabytes of data. To give you some perspective, 1 petabyte is roughly 1,000 terabytes. We're talking about storing the digital equivalent of over 700 million high-resolution photos.
The core entities for search are a user, who creates posts and performs searches; a post, which is the item being searched, has content, a creator, and an implicit like count that changes over time; and a like, created when a user likes a post, where we primarily care about the running count of likes for each post. The APIs for this system are pretty straightforward. For search, it's a getSearch.query the query and sort of likes time, where you specify your search terms and how you want the results ordered.
For create a post, it's a post, sending your content to the system.
And to like a post, you'd use POS like, targeting a specific post by its ID.
Moving to the high-level design, let's start with how users create and like posts in a way that feeds into our search system. For create post, the client sends a ppost request, including the post content, to an API gateway.
The API gateway handles authentication, rate limiting, and routes the request to the post service. The post service then assigns a unique post tide, timestamps the post, and stores its metadata, like content user on created ad, in a database like Cassandra, which is excellent for high write throughput. Crucially, for searchability, the post service also tokenizes the content, breaks it into individual keywords, and pushes these keywords and the post ID to an indexing pipeline via Kafka, a high-throughput message queue.
For like posts, the client sends a POST post like to the API gateway. After authentication, the API gateway routes this to the like service. The like service then increments the like count for that post in Redis for real-time updates and logs the like event to Cassandra for durability, ensuring no likes are lost.
Now, the big challenge: how do users search posts by keyword? We need to be able to find all of the posts which contain that keyword. With trillions of posts and petabytes of data, this is not a small feat. The solution is an inverted index.
The idea behind an inverted index is revolutionary for search. Instead of mapping documents to keywords, it does the opposite. It creates a dictionary which maps keywords to the documents, or in this case, the posts that contain them. Think of it like a books index, but for every word in every book listing all the pages it appears on. We'll keep these inverted indexes in memory using Redis, which makes their queries blazing fast. We're talking milliseconds.
We'll keep a list of all the IDs for posts which match a given keyword as a simple list in Redis. When posts are created, we'll break them apart inside the ingestion service into each keyword that could possibly match, a process known as tokenization, where text is split into meaningful units, and then append that post's ID to the list for each keyword it contains. So if a post says hello world, hello gets the post ID and world gets the post ID.
And how do users get search results sorted by recency or like count? The solution is to have two separate indexes. One sorted by the creation time, which we'll call the creation index, and one sorted by the like count, the likes index. This gives us the flexibility to provide both sorting options efficiently.
Using our Redis-based approach, we can have separate keys depending on whether we're sorting by likes or creation date. For the creation index keys, we can use a standard Redis list. We're always going to be appending new posts to this list, and our queries will only be taking from the last elements, which represent the most recent posts, making chronological lookup very fast.
For the likes index, each key can use a Redis sorted set. A sorted set allows us to keep a list of items ordered by a score, in this case, the like count, similar to how a priority queue works, with efficient insertions and queries for the top items.
When a new post is created, we'll add it to both indexes for every keyword it contains. So if a post contains cat and dog, it gets added to the cat lists in both creation and likes indexes and the dog lists. When a like event happens, we'll update the score in our sorted set for the likes index for that keyword. But here's the problem. Likes are happening quite frequently, 100,000 times per second. Each like event requires us to update many scores so that the like indexes are up to date. This puts a lot of stress on our system, a massive write amplification problem.
Let's delve into those challenges in our deep dives. First, how can we handle the large volume of requests from users for searches?
The solution is to utilize edge caching via a content delivery network, CDN, like Cloudflare or AWS CloudFront. On the response to our search endpoint, we can add cache control headers, which tell our CDN when and for how long to cache a search result.
When a user tries to hit our SERP service, they'll first go through a geographically local CDN host. In the case of a cache hit, these users will get results in tens of milliseconds versus the hundreds which might have been required if they had to go through our API gateway to the search service via a call to the search cache and all the way back. If the result isn't in the cache, the request proceeds as usual. This drastically reduces the load on our backend services for common queries.
Next, how can we handle multi-keyword freeze queries? If you search for Taylor Swift, a direct keyword search for Taylor and Swift separately won't necessarily understand that you want results where Taylor and Swift appear together as a phrase.
To improve read time efficiency for these, we can index bigrams or shingles. These are pairs or sequences of consecutive words in addition to single words. For example, in the sentence, I saw Taylor Swift at the concert, we'd index single words like I saw Taylor Swift at the concert. But we'd also index bigrams like I saw Taylor, and importantly, Taylor Swift, Swift at, and so on.
These bigrams can be added to our likes and creation indexes, allowing us to directly retrieve post IDs for a search like Taylor Swift instead of having to intersect results for Taylor and Swift separately and then trying to figure out if they were close enough. However, this approach significantly increases index size. Bigrams like Swift at are less common and create sparse entries, potentially ballooning from, say, 10 million single-word keys to over 100 million bigram keys, or even more.
To mitigate this explosion in index size, we could index only frequently searched bigrams, falling back to the intersection method when no specific bigram entry exists, using probabilistic structures like count-min-sketch to estimate bigram frequency and only index those that are popular enough. While this reduces index bloat, it does add complexity to the system.
Another big one. How can we address the large volume of writes? When a post is created, we call to the ingestion service, which tokenizes the post, breaks it down into keywords, and then writes the post into the creation and likes indexes. If a post has 100 words, we might trigger 100 plus writes, one for each word.
If a lot of posts are created simultaneously, our ingestion service might get overwhelmed. In the worst case, we might lose posts or events. The solution is, we can address this by adding more capacity to our ingestion service and partitioning the incoming requests. By using a log stream like Kafka, we can fan out the creation requests to multiple ingestion instances and partition the load. We can also buffer requests so that we can handle bursts of post creation. Finally, we can scale out our index by sharding the indexes by keyword. This way, writes to the indexes are spread across many indexes.
That addresses post creation, but the problem of likes volume is even greater. Likes happen far more frequently than post creations. The sheer volume of likes, 100,000 per second, causes high write pressure on the likes index, because each like event requires us to update many scores to keep the like indexes up to date.
The solution is a two-stage approach for likes. To optimize write efficiency, we can update the like count in our indexes only at specific milestones, such as powers of 2 or 10. For example, 1, 2, 4, 8, 16 likes, then 10, 100, then 1,000 likes, etc. This drastically reduces write operations significantly, potentially dropping from 1,000 writes for 1,000 likes to just 10, because you're only updating at specific thresholds, not for every single like.
However, this makes the index inherently stale, though the ordering remains approximately correct. A post with 10,000 likes will still rank above one with 0 or 1 like. To ensure accuracy, we can retrieve the top N2 posts from the like index for a query, pulling a few extra results just in case. Then we fetch the current like count from the like service for each post retrieved. Finally, we resort the results based on the most accurate like count before returning them to the user. This balances performance with eventual consistency.
Lastly, how can we optimize storage of our system? Given the petabytes of data, this is crucial for managing costs and performance.
The solution is tiered storage. We can move rarely used keywords and their associated indexes to a less frequently accessed but ultimately cheaper storage. One way to do this is to move these keyword indexes from their fast, in-memory Redis instance to cold, blob storage like S3 or R2.
On a regular basis, we'll determine which keywords were rarely or not at all accessed in the past month. We'll move these indexes from our in-memory Redis instance to a blob in our cold storage. When the index needs to be queried, we'll first try to query Redis. If we don't get our keyword there, we can query the index from our blob storage with a small, acceptable latency penalty. This means the most popular searches are lightning fast, while older, less common ones might take a tiny bit longer but still function. Hashtag tag collaborative document editor design, like Google Docs.
Let's shift gears now to collaborative document editing, like Google Docs. This is a fascinating problem space because it forces systems to deal with real-time, concurrent changes from multiple users, all wanting to see the same consistent view of a document. The functional requirements here are very specific. First, users should be able to create new documents. Simple enough, right?
But the real magic and the real challenge comes next. Multiple users should be able to edit the same document concurrently. This is where it gets complex because everyone is touching the same content at the same time.
And users should be able to view each other's changes in real time. This is the seamless experience we've come to expect. You type a letter, and your colleague across the globe sees it almost instantly.
And beyond the text itself, users should be able to see the cursor, position, and presence of other users. This provides crucial context for collaboration, letting you know where your teammates are working and who else is in the document with you.
For non-functional requirements, documents should be eventually consistent. This means all users should eventually see the same document state, even if there's a slight delay. It's okay if you see someone's edit a split second after they make it, as long as everyone ultimately lands on the same final version of the document.
Updates should be low latency, ideally less than 100 milliseconds, to ensure a smooth, responsive editing experience. Anything more, and it starts to feel sluggish and disconnected from real-time collaboration.
The system should scale to millions of concurrent users across billions of documents. That's a massive scale, allowing a global user base to work on countless different documents.
However, there's a more constrained and interesting requirement: no more than 100 concurrent editors per document. This simplifies the consistency model significantly. We're not trying to handle thousands editing one document, but still a substantial number.
And crucially, documents should be durable and available even if the server restarts, ensuring no work is lost. You certainly wouldn't want to lose hours of collaborative work because of a system glitch.
The core entities for a collaborative document editor are distinct. An editor is simply a user who is currently editing a document. A document is the collection of text managed by an editor, the actual content.
An edit is a specific change made to the document by an editor, whether it's inserting a character, deleting a word, or formatting text. And cursor represents the position of the editor's cursor in the document, and also the presence of that user within the document, letting others see who is online and where they are typing.
When it comes to APIs, we're going to need lots of bidirectional communication between each editor and the document they're collectively editing. This means we'll definitely need some sort of WebSocket-based approach for the editor experience. A WebSocket is like an open, persistent phone line between the client and the server, allowing messages to flow both ways in real time, unlike traditional request-response HTTP.
For creating a document, a simple POST docs endpoint would suffice, taking a title and returning a document ID. But the real interaction happens over the WebSocket, WS Docs Docketees.
Over this WebSocket, clients will send various operations like type, insert, for text insertion, type, update cursor position, for cursor movement, and type delete for text deletion. In return, the server will receive updates, like type update, for receiving changes from other collaborators. Let's dive into the high-level design. For users being able to create new documents, we'll implement a simple API that takes a title and returns a document ID. For now, we can assume a simple Postgres database because it gives us flexible querying, and if we need to scale, we can always partition and replicate later. Postgres is robust and a good starting point for relational data.
Now, for the central challenge. Multiple users should be able to edit the same document concurrently. Achieving consistency here is not easy. Instead of transmitting the entire document over the wire every time someone makes a change, which would be incredibly inefficient, we can transmit just the edits themselves.
To illustrate the problem, consider this scenario with two users, Alice and Bob, editing the text hello. User A, Alice adds, world at position 5, sending an insert 5, oh world. Simultaneously, user B, Bob, deletes at position 6, sending a deletes. If Alice's edit arrives after Bob's deletion, we end up with hello world, which is correct. But if Bob's edit arrives after Alice's edit without proper handling, deleting at the original position 6 might delete the comma, which is now at a new position due to Alice's insert, instead of the exclamation mark yielding hello world, which is wrong. The document would diverge.
This is where operational transformation OT comes in. It's a remarkably clever technique. The core idea is that each edit is contextual. It's an edit based on a specific state of the document. Dealing with a stream of out-of-order edits from multiple clients presents a bunch of consistency problems. To solve this, we use OT, which essentially adjusts edits based on prior changes to ensure consistency, regardless of the order those edits arrive at the server.
The process involves the server collecting edits and transforming them based on a sequence before applying them or sending them to clients. Let's use our concrete example. Initial text, hello. User A inserts a world at position 5. Hello becomes hello world. User B tries delete 6 for A. Without OT, if Alice's edit arrives first, Bob's delete would now delete the comma, yielding hello world, Wrong. With OT, Bob's delete to 6 is transformed, perhaps to delete 12 because the string length has changed due to Alice's insert, to correctly target after Alice's edit, resulting in hello world. It's like rewriting a command to account for changes that happened since the command was first issued. More. If user C then adds great at position 6, hello world becomes hello great world. Bob's original deletus would now be transformed again, perhaps to delete interest, to correctly target after both Alice's and Chris's edits. The method for OT is to transform operations before applying them locally or sending them to other clients. The pros are very low memory footprint on the server, as you're only dealing with small edits, and fast processing because you're applying precise transformed operations.
The challenges, however, are significant. The server needs to be a central point for ordering and transforming all these operations, which can limit scalability if you have a massive number of concurrent editors on a single document. The implementation is also notoriously complex and error-prone. Getting OT right is a huge undertaking, and it's best suited for small groups of concurrent editors, like our 100 editor limit, not massive-scale collaborative documents with thousands of simultaneous edits.
For our new document operations DB, where we store all these individual edits, we want to use something that we can write to very quickly in an append-only fashion, for now. Cassandra should do the trick due to its high rate, full-put. We'll partition the data by document ID and order by timestamp, which will be set by our document service to ensure global ordering of operations for that document. Once the edit has been successfully recorded in the database, we can acknowledge or confirm it to the user.
Now, how do users view each other's changes in real time? When a user first loads a document, upon the initial WebSocket connection for that document, we push all of the previously applied operations to the client. Since everyone is connecting to the same logical server for that document, this allows us to assume that all connections are starting from the same document state.
When updates happen, if an edit is made successfully by another collaborator, every remaining connected editor needs to receive those updates. Since all of our editors are connected to the same server for that specific document, this is straightforward. After we record the operation to our database, we can also send it to all clients who are currently connected to the same document via their open WebSockets.
It's important to note that on the client side, the user's browser or app also has to perform the operational transformation, OT. When users make edits to their own document, changes are always applied first to their local document to provide instant feedback, and then shipped off to the server.
What happens if another user's edit lands on the server after we've applied our local change, before our local change can be recorded to the server? This is where OT shines. OT gives us a way of handling out-of-order edits. Remember that OT takes a sequence of edits in an arbitrary order and rewrites them so they consistently return the same final document, no matter when they arrived or in what order they were perceived by different clients.
For instance, if user A submits EA to the server and user B submits EB, which might arrive at the server after EA, but user B saw EB first on their screen, the perceived order of operations from each site could be: server sees EA, user A sees EA, EB, user B sees EB, EA. Regardless of this ordering, by applying OT to the operations, we can guarantee that each user sees the same document, preventing divergence and ensuring true collaboration.
Finally, users should be able to see the cursor position and presence of other users. We only really care about where our collaborator's cursor is now, not where it was an hour ago, so this data is ephemeral. It's real-time transient information.
We don't need to keep cursor position or the presence of other users in the long-term document data itself. Instead, we can have users report changes to their cursor position to the document service, which can store it in memory temporarily, and broadcast it to all other users via the same WebSocket.
The document service can also keep track of socket hangups or disconnects, perhaps using heartbeat signals. If a user disconnects, the service removes them from the list of active users for that document and sends a broadcast when it happens to any remaining users. This ensures the presence indicators are always accurate.
Let's get into some deep dives on scaling a system like this. How do we scale to millions of WebSocket connections? This is a huge challenge, as WebSockets are stateful, meaning a single connection must stay open to a specific server.
The solution here is to horizontally scale the document service and use a consistent hash ring to intelligently distribute connections across servers. A consistent hash ring is a clever way to partition data or connections across a dynamic set of servers. Each server in our system joins this hash ring, with each server responsible for a range of hash values. This means we always know both which server is responsible for a particular document based on its ID's hash, and critically, all connections for that document go there. We use Apache Zookeeper to maintain the hash ring configuration and coordinate between servers, ensuring everyone knows who is responsible for what.
Here are the steps for client connection. When a client needs to connect to a specific document, they can initially open an HTTP connection to any of the document servers, potentially via a round-robin load balancer along with the document ID requested. That server will check the hash ring configuration for the given document ID, and if it's not responsible for that hash range, it will respond with a redirect to the correct server's address. This way, clients eventually connect directly to the right server without any inefficient intermediaries.
Once the correct server is found, the HTTP connection is upgraded to a WebSocket connection. The socket server then maintains a map from the document ID to the corresponding WebSocket connections for later use. Finally, we load all the stored operations for that document, if they aren't already loaded, from our document operations DD and are ready to process operations in real time.
The beauty of consistent hashing is that when we add or remove servers from the cluster, only a small portion of connections need to be redistributed. Servers periodically check zookeepers for ring changes and can initiate connection transfers when needed, minimizing disruption. Because the statefulness of WebSockets is a pain to manage across a distributed system, it can be useful to handle them at the edge of your design. By terminating WebSockets early and exposing an internal API to the rest of our system, other services can remain stateless and don't need to concern themselves with the intricate details of WebSocket connections, simplifying the overall architecture.
Next, how do we keep storage under control? Documents could grow infinitely with operations as every single edit is stored. Over time, that can become a massive amount of data.
The solution is to have our document service periodically snapshot or compact operations. Since the document service has exclusive ownership of a document, when we're not actively scaling up the cluster, meaning only one instance is handling a document's operations at a time, we can safely compact operations without worrying about complex coordination or consistency issues.
When the last client disconnects from a document, for example, we can then take all of the existing operations for that document and offload them to a separate low CPU priority process for compaction. This process merges all those individual edits into a single consolidated state of the document. The resulting compacted document state is then written to the DB under a new document version ID, and this document version is updated in the document metadata DB. This efficient process helps manage storage growth over time by periodically cleaning up old granular operations. #tag design a news aggregator like Google News.
All right, let's move on to designing a news aggregator like Google News. This kind of service is all about bringing you information from thousands of sources instantly to keep you well informed. Functionally, users should be able to view an aggregated feed of news articles from thousands of source publishers all over the world.
And naturally, users should be able to scroll through the feed infinitely, just like on many modern social media platforms, providing a continuous stream of content without interruption.
Finally, users should be able to click on articles and be redirected to the publisher's website to read the full content. This is crucial for giving credit and traffic back to the original source, ensuring their business model remains viable.
For non-functional requirements, the system should prioritize availability over consistency, adhering to the CIP theorem. This is suitable for news, where getting some news quickly is better than waiting for perfectly synchronized data. A minute or two of delay for a globally distributed feed is acceptable if it means the service is always available.
The system should be scalable to handle 100 million daily active users, with potential spikes up to 500 million, especially during breaking news events or major global occurrences. That's a huge scale that demands robust architecture.
And critically, the system should have low latency feed load times, aiming for under 200 milliseconds. Users expect fast access to news. Any significant delay makes the service feel sluggish and unusable.
Our core entities for a news aggregator are quite clear. An article represents a news article with attributes like id, title, summary, thumbnail URL, published date, publisher ID, region, and media URLs. This is our core content entity, what we're actually showing to users.
Then there's the publisher, which represents a news source with attributes like id, name, URL, feed URL, and region. Publishers are the origin of our content, the sources we're pulling from.
And finally, the user, representing system users with attributes like id and region, which may be inferred from their IP address or explicitly set by them. Even with anonymous users, we track basic information to serve them relevant content. In terms of table and field structure, the article table would have fields like id, the unique identifier, title, summary, thumbnail, URL for the article's image, publish date, URL to the original article, and so on.
The publisher table would include fields like id, name, URL, the publisher's website, or SS feed where we can pull their articles from, and last scraped, when we last checked their feed, and similar attributes.
Let's get into the high-level design, starting with how users view an aggregated feed of news articles from thousands of source publishers. The data collection service workflow is key here. This service is constantly working in the background. It queries the database for the list of publishers and their RSS feed URLs before querying each one after another.
It then extracts article content, metadata, and crucially downloads media files to use as thumbnails. These thumbnail files are then stored in object storage, like S3, and the article data, complete with media URLs, is saved to the database.
Now, you might wonder why not just point directly to the URL of the source image hosted by the publisher, rather than going through all the effort to download it and store it in our own object storage. That sounds like extra work.
The answer is multifaceted. First, we don't want to rely on the publisher's servers, which may be slow, overloaded, or go down entirely, impacting our user experience. Additionally, we want to be able to standardize the quality and size of the images to ensure a consistent user experience across our entire feed, regardless of the publisher's original image quality. It gives us control over what our users see.
Now that we have data flowing in, we need to serve it to users. For this, we'll add a separate feed service that specifically handles user requests. This feed service handles user feed requests by querying for relevant articles based on the user's region and formatting the response for consumption.
It's important to note that we separate the feed service from the data collection service for several key reasons. They have completely different scaling requirements. The feed service is read-heavy, the data collection service is write-heavy, different update frequencies. Feed service needs real-time, data collection can be more batch-oriented, and different operational needs. Feed service is user-facing, data collection is a background process. It allows each to scale and operate independently.
So when a user requests their news feed, the flow looks like this. First, the client sends a GGT request to feed.region US and limit 20, asking for 20 articles for the US region. The API gateway then routes this request to the feed service.
The feed service queries the database for recent articles in the user's region, ordered by publish date. The database returns article data, including metadata and media URLs pointing to object storage. Finally, the feed service formats the response and returns it to the client via the API gateway.
For users to be able to scroll through the feed infinitely, this is achieved through typical pagination patterns, where new results are loaded as you scroll down, refined in our deep dives for consistency.
And for users to click on articles and be redirected to the publisher's website to read the full content, the browser handles this for us directly. When users click an article, the browser redirects to the article URL stored in our database, taking them directly to the publisher's website. Alternatively, article links could point to Google's tracking endpoint, such as GT_articleID, which logs the click event, useful for analytics, and then returns a 302 redirect to the publisher site. This click data helps train recommendation algorithms and measure engagement.
Let's get into the deep dives. First, how can we improve pagination consistency and efficiency? Simple timestamp-based pagination can have issues with new content arriving with older timestamps or multiple articles having identical timestamps, leading to missed or duplicated results as you scroll.
The solution is a composite cursor. We combine timestamp and article ID to create a unique, totally ordered cursor. For example, 2024 A01 15T10.300123. This string includes both a timestamp and the unique article ID. This ensures total ordering even when articles have identical timestamps, as the article ID provides the necessary tie-breaking mechanism.
The database query then becomes more precise, where publish.articleID cursor timestamp cursor order by publish.say articleID dusky limit 20. This ensures consistent pagination regardless of new content being added and gracefully handles timestamp collisions. The cursor remains stable and predictable, ensuring users never see duplicate articles or miss content due to pagination issues, even if new articles are published in the middle of their scrolling.
Next, how do we achieve low latency, 10 meters feed requests? That's an extremely aggressive speed target for retrieving dynamic content.
The solution involves pre-computed and cached feeds with change data capture, CDC. We pre-compute and maintain feeds for each region in Redis as sorted sets, containing article IDs and essential metadata, organized by region. Redis is an in-memory data store, incredibly fast. When new articles are published, change data capture, CDC, triggers immediate updates to relevant regional caches, rather than waiting for a time-to-live TTL expiration. This means as soon as an article is ingested, it's pushed directly to the cache, bypassing the database for reads.
The flow with CDC works like this. The data collection service stores new articles in the database. This database then triggers CDC events, essentially, a real-time stream of all changes. These CDC events are consumed by feed generation workers that immediately determine which regional feeds need updates based on the article's region and relevance. They then add the new article to the appropriate Redis sorted sets with its timestamp as the score, maintaining chronological ordering automatically.
With the TTL no longer the primary mechanism for freshness because of CDC, we need another way to prevent unbounded cache growth. What we can do instead is maintain only the most recent N articles, typically 1,000 to 2,000 per regional feed. This effectively manages the cache size while always keeping the freshest, most relevant content available for fast retrieval.
Another critical point. How do we ensure articles appear in feeds within 30 minutes of publication? Our current approach of pulling publisher RSS feeds every 3 to 6 hours creates a big problem. By the time we discover breaking news, users have already learned about it from social media, push notifications, or other news sources. This makes our news feel stale.
The solution is to implement webhooks, where publishers notify us immediately when they publish new content. We build a webhook endpoint, for example, POST webhooks article published, that publishers can call the moment they publish an article containing the article metadata, or even the full content payload. This gives us instant updates.
Of course, not all publishers support webhooks. So we'll still keep fallback RSS polling and web scraping for publishers who don't support webhooks, creating a hybrid system that provides real-time updates where possible and regular polling elsewhere. This ensures broad coverage while prioritizing speed for those who can integrate.
What about handling media content, like images and videos, efficiently? We only need to display thumbnails in the newsfeed to make articles visually appealing and help users quickly identify content.
To avoid global users experiencing high latency when loading thumbnails from distant S3 regions, where our main storage might be, we can use a CDN to serve the thumbnails. So we store thumbnails in S3 and serve them through a CloudFront CDN or similar content delivery network for global distribution and low latency to users worldwide. This brings the images physically closer to the users, dramatically speeding up load times.
Finally, how do we handle traffic spikes during breaking news? This is a classic problem in news. A key observation here is that news consumption is inherently regional, with users primarily wanting fast access to local and national news from their geographic region. While some users seek international news, the vast majority of traffic focuses on regional content.
At the app layer for our feed service, the solution is horizontal scaling with auto-scaling groups. We deploy multiple instances of our feed service behind load balancers and use cloud autoscaling to automatically provision new instances when CPU or memory utilization exceeds certain thresholds. Since feed services are stateless, horizontal scaling is straightforward. You can simply add more servers to handle the increased load during a spike, like adding more cashiers during rush hour.
But the database layer, our Redis cache, should drastically reduce the load on our database. All read requests to fetch the feed should hit the cache, meaning our scale challenges are actually offloaded from the database to the cache. This design is highly effective at protecting the underlying database from massive read spikes.
And at the cache layer itself, specifically Redis, the solution is read replicas. Each regional Redis master gets multiple read replicas to distribute the query load. We use consistent hashing to shard the data across multiple instances and ensure each instance has a replica or two to handle the read load and failover.
Write operations like new articles and cache updates go to the Redis master. Read operations for feed requests are load balanced across all replicas using round-robin or release connections algorithms. With Redis Sentinel managing the cluster, if the master fails, one replica gets promoted to master automatically, ensuring continuous availability. It's a robust system designed for constant, high-volume news delivery. #tag design a local delivery service like Gopuff. Let's talk about designing a local delivery service, something like Gopuff, where the emphasis is on aggregating item availability across local distribution centers and preventing double booking of products. This brings unique challenges that blend e-commerce with real-world logistics. Functionally, customers should be able to query availability of items, deliverable in 1 hour by location. This means the effective availability is the union of all inventory in nearby distribution centers, or DCs.
And critically, customers should be able to order multiple items at the same time. This is crucial for a complete shopping experience. You wouldn't want to make separate orders for every single item on your list.
From a non-functional perspective, availability requests should be fast, under 100 milliseconds, to support use cases like searching for items. Imagine typing chips into a search bar. You want to see what's available nearby instantly.
Ordering should be strongly consistent. Two customers should not be able to purchase the same physical product. This is a critical requirement to avoid frustrating user experiences, like ordering the last bag of chips only to find out it was already sold to someone
The
else.
system should be able to support 10,000 DCs, distribution centers, and 100,000 items in the catalog across all those DCs. That's a lot of physical locations and a vast inventory to track in real time.
And the order volume will be on the order of 10 million orders per day. This scale demands a robust design capable of processing a massive number of transactions daily, especially with the strong consistency requirement.
The core entities for this service are inventory, which is a physical instance of an item located at a DC. We'll sum this up to determine the quantity available to a specific user for a specific item. For example, 5 bags of Cheetos at DC Alpha.
An item is a type of item, like Cheetos. These are what our customers will actually care about and search for.
A distribution center is a physical location where items are stored. We'll use these to determine which items are available to a user as inventory is stored within them. It has a geographic location. And finally, an order is a collection of inventory which has been ordered by a user, including all the necessary shipping and billing information. For the APIs, we'll need an endpoint to get availability for a given item and location, and another to place order for selected items. The specific details of these endpoints would be defined in the implementation phase, but these are the core interactions.
Let's move to the high-level design. For customers to be able to query availability of items, we'll introduce an availability service which handles requests from our users for availability given a specific location and any relevant filters, like snacks or drinks.
This availability service will interact with a nearby service. This nearby service constantly syncs with a database of nearby DCs and, crucially, uses an external travel time service to calculate realistic travel times from those DCs to the user's location, potentially even including real-time traffic data, because a 1-hour delivery needs to account for traffic.
The inventory table itself would be a replicated SQL database table which returns the inventory available for each item and DC. This table holds the core truth of what's physically on hand.
To find nearby DCs, we can build a simple internal API which takes a latitude and longitude, lat-long, and returns a list of DCs within a 1-hour delivery radius. Let's assume we have a table of DCs with their lat-long coordinates. Crudely, we can measure the distance to the user's input with some simple Euclidean distance math. A more sophisticated example might use the Haversine formula to take into account the curvature of the Earth, providing a more accurate real-world distance.
The flow for an availability query looks like this. First, we make a request to the availability service with the user's location, X and Y coordinates, and any relevant filters. The availability service then fires a request to the nearby service with the user's location.
The nearby service returns us a list of DCs that can deliver to our location. With the available DCs identified, the availability service queries our database with those DC IDs. Finally, we sum up the results and return them to our client, showing what's available and how quickly.
Next, customers should be able to order items. Our primary goal here is to make sure we're not promising the same inventory to two users, so we need strong consistency. This is where the system absolutely cannot be wrong.
The solution is to put both orders and inventory in the same database, leveraging the AC properties of our Postgres database. ACID stands for atomicity, consistency, isolation, and durability, a set of properties that guarantee valid transactions. By using a singular transaction with an isolation level of serializable, we can ensure that the entire transaction is atomic. This means that if two users try to order the same item at the same time, one of them will be rejected because the transaction will fail to commit if the inventory is not available. This prevents the frustrating scenario of double selling.
There's a disadvantage to this approach, however. While consolidating our data down to a single database for strong consistency has a lot of benefits, it's not without drawbacks. We're partly coupling the scaling of inventory and orders, and we can't always take advantage of the very best, most specialized data store for each specific use case. For example, a NoSQL database might scale inventory checks even better, but then we'd lose strong consistency for orders if they're separate.
For an order, the process looks like this. The user makes a request to the order service to place an order for items A, B, and C. The order service then creates a singular all-or-nothing transaction, which we submit to our Postgres leader. This transaction performs several steps. A. It checks the inventory for items A, B, and C to ensure their quantities are greater than 0. If any of the items are out of stock at this precise moment, the entire transaction immediately fails. C. If all items are in stock, the transaction records the order and updates the status for inventory items A, B, and C to ordered, effectively reserving them. D. A new row is created in the orders table and order items table, recording the specific order for A, B, and CE. Finally, the entire transaction is committed. If the transaction succeeds, we return the order confirmation to the user.
Let's delve into the deep dives for Gopuff. First, make availability lookups incorporate traffic and drive time. This is crucial for that 1-hour delivery guarantee.
To do this, we can sync periodically, like every 5 minutes, the DC location data from a DC table to the memory of our nearby service. When an availability input comes in, we can prune down the candidate DCs by taking a fixed radius, say 60 miles, representing the most optimistic distance we could drive in 1 hour, and limiting ourselves to only evaluating those. We'll take these restricted candidates and then pass them to the external travel time service to create our final real-time estimate, factoring in current traffic conditions.
Second, make availability lookups fast and scalable. We need these checks to be almost instantaneous. One solution is to query inventory through cache. We can add a Redis instance to our setup. Our availability service can query this cache for a given set of inputs and, if the cache hits, return that result immediately, typically in single-digit milliseconds.
If the cache misses, we'll then do a lookup on the underlying database and then write the results into the cache for future requests. Setting a low TTL, time to live, for these cached results, for example 1 minute, ensures that these results are fresh enough for availability checks without constantly hitting the database.
Alternatively, since we only ever read inventory from a nearby collection of DCs, we can group them together with a region ID, perhaps using the first 3 digits of their zip code. Then we can partition our inventory database based on these region IDs. This means most queries will go to mostly 1 or 2 partitions rather than querying the entire inventory dataset, significantly reducing the query scope and speeding things up.
We can also use read replicas for availability, since we can tolerate a small amount of inconsistency in availability checks. Our orders, which need to be strongly consistent, will still have those transactions sent to the Postgres leader. But our availability queries can go to our read replicas, offloading a significant amount of read load from the primary database, keeping it free for critical order processing. ## photo sharing app design like Instagram. All right, let's talk about building a photo sharing app like Instagram. This is a fascinating system because it combines massive media storage with social networking and real-time feed delivery. Functionally, users should be able to create posts featuring photos, videos, and a simple caption. This encompasses all the media types that make a social feed visually rich.
Users should also be able to follow other users, establishing their social network within the application. This forms the basis of whose content they see in their feed.
And critically, users should be able to see a chronological feed of posts from the users they follow. This is the primary consumption experience, a constantly updating stream of content from their social circle.
For non-functional requirements, the system should be highly available, prioritizing the availability of photos and videos over strict consistency. Eventual consistency is fine here, with an allowance of up to 2 minutes of staleness. It's better that you can always see your feed, even if a new post from a friend appears a minute or 2 after they hit publish.
The system should deliver feed content with low latency, aiming for under 500 milliseconds end-to-end response time for feed requests. No one wants to wait for their photos to load or their feed to refresh.
And of course, the system should render photos and videos instantly, ensuring low latency media delivery for an optimal user experience. High-quality media needs to appear almost immediately as you scroll.
The system must be scalable to support 500 million daily active users, DAU. That's a massive user base, almost 500 million people interacting with the service every single day, generating immense traffic and data. Our core entities for a photo sharing app are a user with a username, profile details, and so on. A post, which crucially is a single entity handling both photos and videos, referencing the actual media file and including a caption and the user who created it.
The media itself represents the actual bytes of the photo or video file, and we'll plan to use S3 for this, which is a highly scalable and durable object storage service. And finally, follow, which represents the unidirectional relationship between 2 users, where one user, the follower, is following another user, the followee.
For the APIs, to create posts, we'd have a POSI posts endpoint that returns a post ID as a unique identifier for the new post. The actual upload of a photo or video will be handled separately using a pre-signed URL technique we discussed earlier, allowing direct, secure upload to storage.
To follow other users, a POST follows endpoint would be used. The follower's ID would be extracted from the authentication token, like a JWT or session token, so we don't need to specify it in the request body, making the API simply and more secure.
And to see their feed, A GET feed.cursor-in-limit page size endpoint would return an array of posts, allowing for efficient pagination and infinite scrolling.
In the high-level design for users creating posts featuring photos, videos, and a simple caption, the steps are: first, the client makes a post request to the API gateway with the media and caption.
The API gateway routes the request to the post service. The post service receives the media and caption, stores the post metadata in the database, and crucially, stores the actual media bytes in a blob store like S3.
Finally, the post service returns a posted to the client, confirming the creation and giving them a reference to their new post.
Next, for users being able to follow other users. Given the scale, the limited relationships, just who follows whom, and the fact that eventual consistency is acceptable, we're going to go with DynamoDB. It's a highly scalable NoSQL database well-suited for this type of access pattern.
Since we're opting for DynamoDB, we'll need to add a few indexes to our tables to avoid inefficient full table scans. For the follower table, we'll make the partition key the follower id and the sort key the follow id. This allows us to efficiently query for all users that a given user follows.
For the post table, we'll make the partition key the user id, since most of our queries will be to get the posts of a given user. We can make the sort key a composite of created at and posted at to ensure chronological ordering while maintaining uniqueness. However, if a user is following thousands of people, this one-by-one extraction from the database would be incredibly slow, even with indexes, which brings us to our next deep dive.
The challenge of users seeing a chronological feed of posts from the users they follow is directly addressed in our deep dives for scalability and latency, which we'll discuss next. This is truly the core of what makes a photo-sharing app work at scale.
Let's jump into the deep dives, because this is where the really complex stuff comes in. The system should deliver feed content with low latency, 500 meters. This is where a key architectural decision makes all the difference.
The solution is a hybrid fan-out approach. We combine fan-out on write for most users with fan-out on read for popular accounts. This provides a good balance. Fast reads for the majority of users and manageable write amplification for accounts with millions of followers.
We define a threshold for the number of followers, say 100,000 followers. For users with fewer than 100,000 followers, we pre-compute their followers' feeds. So when they post, their post is added directly to their followers' pre-computed feeds. This means when a follower opens their app, their feed is already ready, waiting for them.
For users with more than 100,000 followers, whom we might call the celebrities or influencers, we don't pre-compute their posts into their followers' feeds. Instead, when a celebrity posts, we simply add the post to the posts table and do not trigger an asynchronous feed update for their millions of followers, preventing massive write operations.
When a user requests their feed, we first fetch the pre-computed portion of their feed from Redis, which contains posts from users with fewer than our 100,000 follower threshold. Then we also query the posts table for recent posts specifically from the celebrities they follow. Finally, we merge the pre-computed feed with the recent post from celebrities chronologically and return the combined feed to the user. This is done on the fly at read time.
There are critical trade-offs here. The 100,000 follower threshold needs to be carefully tuned. Set it too low and we don't solve the write amplification problem. Set it too high and we impact read performance for too many users. Users following many celebrities might experience slightly slower feed loads than those who don't, creating an inconsistent user experience. We'll need to set clear service level agreements, SLAs, for different user segments and potentially implement additional caching specifically for celebrity posts to mitigate this.
When proposing Redis as a feed storage solution in your system design, it's crucial to proactively address durability concerns. What happens if your Redis instances go down and all those pre-computed feeds are lost? You could explain that you'd implement Redis Sentinel for high availability with automatic failover, potentially use Redis Cluster for data sharding across multiple nodes for even greater scale, and configure persistence options like AOF append-only file or RDB snapshots to recover data after failures, ensuring your feed data isn't permanently lost.
Next, the system should render photos and videos instantly, supporting photos up to 8 MB and videos up to 4 GB. This is a big challenge for media-heavy apps, especially considering global users and varied network conditions.
The solution is to combine CDN distribution with dynamic media optimization. When media is uploaded, we use a media processing service, like Cloudinary or Imgix, to generate multiple variants optimized for different devices and network conditions. For images, this includes different resolutions, e.g., small for mobile, large for desktop, and formats like WebP for supported browsers, which offers better compression. For videos, we create multiple quality levels and use adaptive streaming so users receive the best quality their connection can handle.
The CDN then serves these optimized variants based on the requesting device and network conditions. Mobile users automatically receive appropriately sized images, while desktop users get higher resolution versions. The client typically includes device information and network conditions in its requests, allowing the CDN to serve the most appropriate variant from the closest edge location.
We also implement intelligent caching strategies. Popular media is cached more aggressively at edge locations, CDN servers closer to users, while less access content might have shorter TTLs or be evicted sooner. For viral content that suddenly gains popularity, we can proactively warm caches in regions where we predict high viewership, preloading content to ensure instant delivery.
Finally, the system should be scalable to support 500 million DAU. This massive user base touches almost every component we've discussed.
The pre-computed feeds hybrid approach is the cornerstone of our scalable feed generation. By pre-computing feeds for the vast majority of users, those following accounts with fewer than our defined threshold of followers, we drastically reduce read-time load on the database. The real-time merging for celebrity posts is a carefully considered trade-off to manage write amplification while still providing an up-to-date experience.
Using a content delivery network, CDN, like CloudFront for media delivery, is essential for global scalability and low-latency access. It offloads huge amounts of traffic from our core servers. Dynamic media optimization further improves performance for diverse devices and network conditions, enhancing the user experience.
For large files, especially videos, chunked uploads are vital. This technique, breaking files into smaller pieces, improves reliability. If a chunk fails, only that chunk needs to be resent, enhances the user experience with progress indicators, and allows for parallel uploads, speeding up the process.
Our database choice and indexing, like DynamoDB or a similarly scalable NoSQL database, provides horizontal scalability for metadata storage. The careful use of partition keys and sort keys ensures efficient queries even with a massive dataset.
And for cost optimization, which is always a concern at this scale, we can always move the media that has not been accessed in a long time to cheaper archival storage like Glacier. Similarly, if we grow concerned about the price of DynamoDB for very cold metadata, we can move infrequently accessed data over to S3 for even more cost savings. Design a distributed job scheduler like Airflow. Our final deep dive for today is into designing a distributed job scheduler. Something like Airflow. It is not about what you see on your screen, but the invisible backbone of many digital operations. It's a program that automatically schedules and executes jobs at specified times or intervals, used to automate repetitive tasks, run scheduled maintenance, or execute complex batch processes in the background. Think of it as the ultimate digital taskmaster.
Let's define the core concepts here. A task is the abstract concept of work to be done. For example, send an email or process daily sales reports. Tasks are reusable and can be executed multiple times by different jobs.
A job is an instance of a task. It is made up of the task to be executed, the specific schedule for when the task should be executed, and any parameters needed to execute the task. For example, if the task is send an email, then a job could be send an email to John at example.com every Friday at 10:00 a.m.
Functionally, users should be able to schedule jobs to be executed immediately at a future date, or on a recurring schedule, i.e. every day at 10:00 a.m., or the first Monday of every month. This flexibility is key.
And users should be able to monitor the status of their jobs. This is crucial for operational visibility. You need to know if your automated processes are succeeding, failing, or still running.
For non-functional requirements, the system should be highly available, prioritizing availability over consistency. It's more important that the scheduler is always running and trying to execute jobs, even if there's a slight delay in its internal state being perfectly synchronized.
The system should execute jobs within 2 seconds of their scheduled time. That's a very tight precision requirement for a distributed system, especially when dealing with thousands of jobs per second. This often implies real-time processing capabilities.
It should also be scalable to support up to 10,000 jobs per second. That's a significant throughput, requiring careful design to avoid bottlenecks in scheduling, queuing, and execution.
And finally, the system should ensure at least once execution of jobs, meaning a job is guaranteed to run even if it runs more than once in rare failure scenarios. While exactly once is the ideal for some systems, for a job scheduler, ensuring it runs at least once is often the priority, as downstream systems can typically handle duplicate processing.
Our core entities are task, representing the reusable work definition. Job, an instance of a task with a specific schedule and parameters. Schedule, which can be a serial-on expression, a standard way to define recurring times, or a specific date time, and user, who schedules and monitors these jobs.
The APIs would typically include endpoints to create a job, setting the task schedule and parameters, and to check the status of our jobs, to monitor their progress.
Let's trace the data flow, the journey a job takes through our system. A user schedules a job by providing the task to be executed, the schedule for when the task should be executed, and the parameters needed to execute the task.
That job is then persisted in the system in a database, ensuring it's not lost. It's then picked up by a worker process and executed at the scheduled time.
If the job fails for any reason, it is retried with exponential backoff, meaning it waits a bit longer between each retry attempt. And throughout this process, we update the job status in the system so users can track its progress or failure.
Moving to the high-level design for scheduling jobs. The user makes a request to a job's endpoint. We store the job definition in our database with an initial status of pending. For a system with no strong consistency needs and our data has few rigid relationships, we're going to opt for a flexible key-value store like DynamoDB to make scaling later on easier due to its horizontal scalability.
We split our data into two main tables. First, our jobs table stores the job definitions. Its id, the user id who created it, the task it executes, any parameters it needs, and its schedule. This is the blueprint for the job.
Then, our executions table tracks each individual time a job should run. It has fields like time, when it's due, job id, linking back to the definition, user id, status, pending, running, complete, failed, and attempt, how many times it's tried to run. By using a time bucket, a Unix timestamp rounded down to the nearest hour, as our partition key, we achieve efficient querying while avoiding hot partition issues. For example, to find jobs that need to run in the next few minutes, we only need to query the current hours bucket and possibly the next hours bucket, significantly narrowing the search.
When a worker node is ready to execute jobs, it simply queries the executions table for entries where the execution time is within the next few minutes and the status is pending. It pulls batches of these jobs to start processing.
For monitoring the status of jobs, the typical statuses would be completed, failed, in progress, or retrying. But how can we efficiently query for the status of all jobs for a given user? With the current design, querying jobs by userid would require an inefficient two-step process. You'd have to query the jobs table to find all jobids for a user, which could be an inefficient full table scan if you have many users, and then query the executions table to find the status of each individual job. That's too slow for a real-time monitoring dashboard.
To solve this, we'll add a global secondary index, GSI, on the executions table. The partition key for this GSI will be userid, and the sort key will be a composite of execution time plus jobid. This allows for incredibly efficient lookups of all jobs belonging to a specific user and their status, ordered by when they were executed, making monitoring much more responsive.
Let's dive deep into the challenges. First, how can we ensure the system executes jobs within 2 seconds of their scheduled time? Querying the database every few minutes to find jobs that are due for execution is not going to work for that level of precision. Databases aren't designed for sub-second real-time polling of scheduled events at massive scale.
The solution is a two-layered scheduler architecture which marries durability with precision. Phase 1. Query the database. Just like in our current design, a cron job runs periodically, say every 5 minutes, to query the executions table for jobs that are due for execution in the next 5 minutes, leaving some buffer for network latency, etc. This pulls all the jobs coming up soon.
Phase 2. Message queue. We'll take the list of jobs returned by our query and push them to a message queue, ideally one that supports delayed delivery, ordered by execution time. Workers will then pull jobs from the queue in order and execute the job when it's due. By running database queries just once every 5 minutes, we drastically reduce database load while maintaining precision through the message queue. The message queue's high throughput and ordering guarantees mean we can execute jobs with sub-second precision because it handles the countdown.
But what about new jobs that are created and expected to run in less than 5 minutes? They won't be picked up by the 5-minute cron job. We could replace our simple log-based message queue with a queue system that can handle job prioritization based on execution time and immediate delivery. Amazon SQS provides a fully managed queue service with native support for delayed message delivery called an SQS delivery delay. When scheduling a job, we simply send a message to SQS with a specific delay value, and SQS handles the rest, delivering the message to our worker exactly when it's needed. For instance, if we want to schedule a job to run in 10 seconds, we can send a message to SQS with a delay of 10 seconds. SQS will then deliver the message to our worker after the delay. This system also offers dead letter queues to capture failed jobs for investigation. High availability is guaranteed across multiple availability zones, and the service scales automatically to handle our load.
So the two-layered scheduler architecture using SQS works like this. First, a user creates a new job, which is written to the database. Second, a cron job runs every 5 minutes to query the database for jobs that are due for execution in the next 5 minutes.
Third, the cron job sends these jobs to SQS with appropriate delay values. Fourth, workers receive messages from SQS when they're ready for execution. And finally, if a new job is created with a scheduled time less than 5 minutes from the current time, it's sent directly to SQS with the appropriate delay, bypassing the cron job and ensuring it's picked up quickly.
Next, how can we ensure the system is scalable to support up to 10,000 jobs per second? To support this, we address bottlenecks starting with job creation. Assuming most jobs are one-time executions, job creation could indeed hit 10,000 jobs per second. Scaling the job creation service horizontally, adding more instances, and using a scalable database like DynamoDB or Cassandra handles this load effectively. A message queue, for e.g. Kafka or RabbitMQ, could buffer spikes but may overcomplicate unless complex logic requires it. Scaling the service and database directly is simpler.
For the jobs database, DynamoDB or Cassandra scales very well with jobs table, partitioned by Jobit for load distribution, ensuring no single server becomes a bottleneck for writes. Executions table, partitioned by execution time for efficient querying, as we discussed with time buckets. Proper provisioning of these databases supports 10,000 operations per second or more, with archiving old data to S3 after a year for cost savings.
For the message queue, SQS, in a 5-minute window, 3 million jobs, 10,000 jobs per second, x 300 seconds, generate approximately 600 megabytes of data, assuming 200 bytes per job. AWS SQS auto-scales to handle this, though it may require a quota increase from the default 3,000 messages a second for very high throughputs. Multiple queues may separate job types, but not primarily for scaling.
When it comes to workers, the machines that actually execute the jobs, we have a crucial choice between containers, like those managed by AWS ECS or Kubernetes, and Lambda functions, serverless compute. For containers, they are best for steady, long-running workloads. Their cost model is more cost-effective for high volume. Scaling is elastic, but perhaps less instant than Lambda. Performance is consistent, with no cold starts, but they have higher operational management overhead. The benefit is they can maintain state between executions if needed.
Lambda functions, on the other hand, are best for short-lived, event-driven jobs, typically under 15 minutes. Their cost model can be expensive for sustained, high-volume workloads. Scaling is instant and auto-scales on demand. Performance has potential for cold start latency, a slight delay when a new function instance spins up for the first time. Overhead is minimal operational overhead. You just upload your code. The downside is they are stateless by nature.
For a steady, predictable workload of 10,000 jobs per second requiring 2-second precision, containers are generally the better choice. They offer a better balance of cost-effectiveness and performance for this type of high-volume, long-running task, allowing for more controlled resource allocation and predictable execution times.
Finally, how can we ensure at least once execution of jobs? Jobs can fail within a worker for one of two reasons. A visible failure, where the job fails visibly in some way. Most likely this is because of a bug in the task code or incorrect input parameters. The job itself throws an error.
Or an invisible failure. The job fails invisibly. Most likely this means the worker itself went down unexpectedly, perhaps the server crashed, and the job just stopped without reporting an error.
For visible failure, we implement robust error handling by wrapping task code and try-catch blocks to gracefully catch failures. For logging and status update, we log errors, update job status to retrying in the executions table, and track the attempt count.
For retry mechanism, we requeue the job in SQS with exponential backoff, which is handled by SQS automatically, so it doesn't immediately overwhelm the system. And we set a retry limit, perhaps up to 3 times. If it still fails after that, we mark its status as failed in the executions table and stop retries, preventing an endless loop.
For invisible failures, this is where SQS visibility timeout comes in. When a worker receives a message from the queue, SQS automatically makes that message invisible to other workers for a configurable period, called the visibility timeout. The worker processes the message and deletes it upon successful completion. If the worker crashes or fails to process the message within the visibility timeout period, SQS automatically makes the message visible again for other workers to process, ensuring it's not lost.
We can set a relatively short visibility timeout, for example 30 seconds, and have workers periodically heartbeat by calling the Change Message Visibility API to extend the timeout as long as they are still working on the job. This way, if the worker crashes, other workers can pick up the job within 30 seconds rather than waiting for a longer timeout to expire, ensuring quick recovery.
And how do we ensure our task code is idempotent? In other words, running the task multiple times should have the same outcome as running it just once. This is crucial for at least once delivery, as you don't want side effects from duplicate runs.
The solution is to design jobs to be naturally idempotent by using idempotency keys and conditional operations. Each job execution includes a unique identifier that downstream services can use to deduplicate requests. For example, when processing a payment, you'd include a unique transaction ID. If you receive the same ID twice, you know it's a retry and you don't process the payment again, only confirm the original one. This prevents unintended side effects from retries.
Here's where it gets really interesting. We've just navigated a whirlwind tour through the architectural blueprints of some incredible complex systems that underpin our digital lives. From ensuring every message is delivered reliably, to making sure your shared vacation photos load instantly across the globe, and even orchestrating millions of background tasks with precision, it's all about thoughtful design.
What stands out to you? We've seen recurring themes. The dance between availability and consistency, recognizing that for many user-facing systems, being always available, even with slight delays, is often preferred over perfect, instant consistency. We saw the critical role of caching and CDNs for low latency, bringing data physically closer to users, and the power of data partitioning and sharding for scalability, allowing systems to grow infinitely by dividing and conquering. Lastly, the importance of asynchronous communication to keep things flowing smoothly, preventing one slow component from bringing down the whole system. Every decision, every design choice is a trade-off aimed at optimizing for specific user experiences and operational needs.
So what does this all mean? It means that beneath the polished interfaces of the apps and services you interact with daily, there's a world of ingenious engineering. Understanding these underlying patterns not only deepens your appreciation for technology, but also equips you with powerful insights, whether you're building the next big thing or simply trying to make sense of the digital landscape around you. The seemingly simple acts online, sending a message, sharing a photo, or ordering groceries, are a symphony of meticulously designed components, constantly working in concert to deliver the seamless interactions we've come to expect. Next time you use an app, pause and consider the invisible architecture making it all possible. Keep exploring, keep questioning, because there's always more to learn in the deep dive.